So after running the main function, you get options for the different test cases. Let's run one. In this case, to the left over here are the moves that are done before the game starts. And then at the right of this, you'll have the different player moves. And in this case, I did Dance to 1-1 and I won. If I run it again on test case 2, the initial moves and then the next moves that the various players do. And in this case, I lost. And if we run 3, it takes a little bit longer because there's a higher branching factor. But I won that version. And if you go to the right, you can see all of the actual moves that are performed. So Dance Puzzle extends the puzzle class that I wrote for the previous assignment, and the state space is a 2D array of booleans. In the constructor, there's some accounting for the moves that occur before the AI start playing. So that happens in the constructor. And then the successor function will essentially visit the current state and figure out all of the possible moves for elements. Essentially, elements in the 2D array are false based on the previous player's second move. The test goal, so the player or the game is done when there are no successors to the current node in the state space. There are 2 heuristic functions, and dance is the function that adds, that modifies the state space in order to record that a move has occurred. I wrote min-max to be iterative, and so what has to happen is in the constructor, there is some accounting for who plays first depending on the number of moves. And then solve, you have, it's just going to be a sequence of moves until somebody wins. So player 1 will search the puzzle to a certain depth, and then, right, and that happens here. And then if he solved the puzzle, then he wins. Otherwise, player 2 works on the puzzle that player 1 has just given to him, and then solve runs on that. And this occurs until either player 1 or player 2 wins. The actual method by which each player searches the state space is this DFS-MM, which is a depth-limited depth-first search function with min-max and alpha-beta pruning. So all of those things that I talked about happen in the add to node list function. Again, this is iterative, so a lot of accounting is going on here. What happens is after a node is popped from the list, if its successors need to go on the list, this function gets called. If the successor has a greater depth than the limit, then nothing has to be done. Obviously, at the root, no matter what happens, that node should be added to the node list. If the node being added is either a test goal or is at the maximum depth, at that point, evaluate the heuristic function and set that node to have that value. And if its parent has no heuristic value, set the heuristic value for that parent. For all of the other nodes, if the parent has no value, then that child can safely be added to the node list. And in the case where the parent already has a heuristic evaluation, then depending on if it's an even or odd depth, then a determination has to be made whether or not that node gets added to the list. So in this case, if the parent is at an even depth, the parent is max. And so if the child's heuristic is greater than the parent's heuristic value, then that child needs to be added to the node list. Otherwise, it's a pruned node. If the parent is a minimum node, then the same logic applies. If the value of the child is less than that of the parent, then change the heuristic value of the parent and add that child to the node list.